Today we're going to go over the electron configurations and Lewis dot structures. So we looked at last week the atomic theory, the modern atomic theory, and in that you learned about Bohr's model. And Bohr's model talked about the energy levels, that electrons fill different energy levels. And that was very true, and it was a great model for the time. But then what ended up happening is scientists started to realize that there were some holes in that theory and that it couldn't accurately predict the behavior of the elements based on the electrons. So eventually we had Schrodinger's quantum mechanical model. And Schrodinger based this on the probability of finding the location of an electron. Now, here's the deal. This is something that I learned in my upper division chemistry classes when I was at UCSD, but you're not going to go into that much detail. So we're not going to look at the mathematical equation. So in high school, you start to learn the quantum mechanical model, but then you start to build on that as you move further along with your knowledge in chemistry. So from the quantum mechanical model, we've developed electron configurations. And what electron configurations are is they're these devices, or you write out basically the address of an electron. And it's kind of like your address. So your address could be 253 Cuyamaca Drive, Santee, California, 92071. Whatever your address would be, that would be like finding the electron configuration of you, okay? So the electron configuration figures out where the electron is in the neighborhood, okay? And this helps us to understand the chemical reactivity of elements. It also, something else that's important to note is that electrons behave as both a wave and a particle. So when we're looking at electron configurations, we need to understand that electrons are going to fill energy levels and then they're going to fill orbitals. So orbitals are like your location in your neighborhood. And something that's important with your orbital is to understand that each orbital can only have a maximum of 2 electrons per individual orbital. So when we're looking at these, so if we look at the S orbital, S only has 1 orbital, and so you can only have 2 electrons in S. P has px, see how it's on the x-axis, pz, and also py. So the P sublevel can have you have 2 electrons here, 2 electrons there, and 2 electrons there. So you can have a maximum of 6 total in the P sublevel, okay? And then we have D. You start to get these funky shapes, but D has 1, 2, 3, 4, 5 different orbitals. So you have a maximum of 10 electrons that can fill the D sublevel. And then you have F, which has 7 across. So you can have a maximum of 14 electrons total in that entire F sublevel. So going back to some terminology, we have the energy level. Energy level tells us how far away an electron is from the nucleus. Then we have the sublevel. The sublevel kind of tells us what block, like what the shape of the orbital is, but what block on the periodic table you can find your element in. And we'll talk more about that later. So that sublevel is either S, P, D, or F. And then you have orbitals. So each sublevel has a different number of orbitals. S again has 1, P has 3, D has 5, and F has 7. Wanting to make sure that you see that the S sublevel can have a maximum of 2, P can have a maximum of 6, D 10, and F 14. And I'm going to show you how you can tell that or remember that just by looking at your periodic table. So I really believe that you use the periodic table for writing your electron configurations constantly. I just think it's much easier to understand how to write them when you're looking directly at the periodic table. So hang with me, okay? You have in your sublevels have your different orbitals. So you have your 1 orbital for S, 3 orbitals for P, 5 for D, and 7 for F. And then each sublevel is going to start at a different energy level. So in the energy level 1, you only have S. Energy level 2, you have S and P. And energy level 3, you have S, P, and D. And then energy level 4, you have S, P, D, F. And those are your different sublevels. And again, just hang tight and I'll explain further. Okay. So the quantum mechanical model assigns electrons a quantum number. Okay. And quantum numbers are split up into four different things, four different quantum numbers. So you have your principal quantum number, which is your energy level. And again, that tells you how far away you are from the nucleus. Angular momentum quantum number is it S, your P, or your D, or your F? So that's your sublevel. Your magnetic quantum number is the orientation of that. So is that your PX, PY, PZ? And then finally, your spin quantum number is your electron going up a half spin or is it going down a half spin? You don't need to remember the name of the quantum number. So you don't need to remember principal quantum number, angular momentum. You also don't need to remember N, L, M, or S. Okay. I'm only putting that on here just so that you understand the theory behind it, or you kind of have an introduction to the theory behind it, just so that if you were to ever use it again or be shown it again, you're going to be able to perform it and understand what maybe a professor is talking about. So moving on from here, okay, I like to use a hotel analogy for this one, okay? And the hotel analogy that I use is, so I have this hotel that I go and visit, and in this hotel, there are no elevators. So I need to use the stairs, okay? And so my hotel, in this analogy, my floor number represents my energy level. So how far away am I from the front desk? Or think about it this way. What about those hotels that provide breakfast in the morning? So how far away are you from the food? Okay. And then your room is going to be your sublevel or your angular momentum. Your room is going to be like your S, your P, your D, or your F, because every single hotel has different classifications of rooms, right? So you have a single room, you have a double room, you might have a suite. So you have all of these different types of rooms. So your room type is going to be like your sublevel. So your room is going to be your S, your P, your D, or your F. And then your number of beds, the number of beds is your orbitals. So for example, when I'm looking at a room S only has one bed. Room P has 3 different beds that you can sleep in. Room D has 5 different beds. Okay. So if you're hopefully starting to catch on, your beds are your orbitals. And then finally, your direction of your sleeper. So the way I look at this is one time I was hanging out with some friends in the desert, and this was years and years ago, and we were kind of doubling up on beds, and so we had the guys were sharing a bed. So then other people didn't have to share a bed. So these 2 guys were sharing a bed, and I looked up and they were sleeping head to toe and head to toe. And the explanation that they gave me was, you don't want to wake up looking each other in the eyes. So it kind of made me think, well, that's how electrons behave in an orbital. So one electron will spin up, one electron will spin down. Okay. And we call those half spins. Now, here's the deal. There are 3 different rules in how electrons fill energy levels or fill orbitals. First, you have the Aufbau principle. Aufbau principle says, you want to fill the lowest energy level first. So a hotel manager is going to fill the lowest energy level first, or the lowest floor first, because it's easier to clean the rooms in the first floor since this hotel doesn't have any elevators. Also, the people who are staying there only want to fill the lowest energy level first because they don't want to lug all their luggage up those stairs, right? So it's going to be way more work, take way more energy to get to another energy level. And so people want to fill the first floor first and then move on from there. Pauli exclusion principle. The hotel manager tells you that you can only have a maximum of 2 people per bed. Do people always follow that? No. I grew up with 7 kids in my family. So we had kids like sleeping in bathtubs, for goodness sake. So, but if you think about it, how many are you supposed to sleep in a bed? Technically, you're supposed to sleep 2 people per bed in a hotel. Okay. And then Hund's rule says that electrons are going to occupy an orbital first of equal energy. And then 1 electron is going to enter an orbital first. And then until all of the orbitals have an electron in them. And then all of a sudden, you're going to fill in the orbitals before you go get another room. So the way I look at this is, say you had 3 people in your family. Okay. Say you had, your mom, your brother, and yourself, and all 3 of you were going on vacation, and you get to a room and the room has 3 beds. So all of a sudden you run into the room and it's like, I've got this bed, I've got this bed, and I've got this bed. And I mean, that's how it is when we go to hotels. My son will, claim his bed. But here's the deal, is that you're not going to share a bed with your brother or your sister unless you absolutely have to, right? So everyone's going to fill in a bed or claim a bed first, and then you're going to fill in those beds. So fill across, so 1 person per bed, and then fill in to make it 2 people per bed. Maximum in that case would be 6 people. Okay. And you can see a visual of that right here. So Hund's rule says this is how you're going to fill an orbital. This is not how you're going to fill. This is absolutely wrong. You don't double fill before you go in. Okay. Or you don't fill before you go across, because you have this empty space right here. Right. And so this electron right here is going to come up over here. And what that does, so that we can stop here and really look at this diagram, what that does is that leaves space to, say you guys wanted to bring a friend, okay? 1 friend, 2 friend, or 3 friend. And so the thing is that those indicate spots for bonding, okay? Another thing that this diagram shows us is whatever element this is has 1, 2, 3, 4, 5, 6, 7 electrons. So you could, if you're doing this along with me, you could check out your periodic table real quick, and you could tell me what element has 7 electrons in it. 7. 1, 2, 3, 4, 5, 6, 7. And if you look real closely, you can see that nitrogen has 7. So that's actually the electron configuration for nitrogen, okay, on the periodic table. So let's look at some more information. Okay, taking a look at this diagram right here. So this is how we're going to look at electron configurations. And if you have a periodic table that you have printed up, I highly suggest you color your periodic table in the different blocks. So for example, I would color this block right here. I would color this block your S block, okay? And then I would color this block right here, your P block, okay? And then this one right here is going to be your D block, okay? And then down here, your lanthanides and actinides are going to be your F block. Now, here's the deal. Remember how I told you that you could look at the periodic table and determine the maximum number of electrons per sublevel? Well, if you look at S is 1, 2 across. P is going to be 1, 2, 3, 4, 5, 6 across. D, you figured it, is going to be 10 across. And then F is 14 across. And the thing about that is, if you take that number and divide by 2, that tells you how many orbitals are also in that sublevel. So I think that you can just really use the periodic table for pretty much anything that you need when it comes to electron configurations. So what we're going to do is we're going to look at some examples. So it says strictly using the periodic table, write the electron configuration for silicone. So I'm going to find silicone here, and silicone is number 14 on the periodic table. So I'm not going to say 1s and then 1s. Instead, I'm going to make that easier on myself. I have 1s and 1s. So I'm going to say that silicone is 1s2 because I have 2 electrons in my 1s. Okay. Then I have my 2s right here. This is going to be 2s2. Then I go across here to P, just like reading a book. You're going to move left to right and then go down the next row. So then I have 2p, and how many electrons did I have in that? I had 1, 2, 3, 4, 5, 6. So that's going to be 2p6, Okay. And then I have 3s2. And then I have 3p2. Okay, so my electron configuration for silicone is 1s2, 2s2, 2p6, 3s2, 3p2. So the two on the top here, okay, the two on the top, my exponent right there, those represent all of the electrons that are there. Okay, so if you counted all of those electrons, I have 2 plus 2 is 4, and then I have plus 6 is going to be 10, and then plus 2 is 12, and then plus another 2 is going to be 14. So I have 14 electrons, and a neutral atom of silicone has 14 electrons. So again, the electron configuration for silicone would be 1s2, 2s2, 2p6, 3s2, 3p2. Okay, so let's try another one. Okay, what if I wanted to go even more simple? What if I wanted to talk about oxygen? Okay, oxygen has 8 valence electrons. I'm going to use hydrogen. I'm going to cross the electrons for hydrogen and helium. So for oxygen, I have 1s2, okay, then 1, 2, 2s2, and then my last one would be 2p1, 2, 3, 4, 2p4. Okay, so for oxygen, we have 1s2, 2s2, 2p4. Okay, and if you add those electrons together, you get 2 plus 2 is 4 plus 4 is 8. And a neutral atom of oxygen is going to have 8 electrons. Okay, now let's look at, say I wanted to go down to vanadium. And you'll look, if you notice on the periodic table, there's something funky on here. You'll notice that when you go, if you look on the left-hand side, you go from 4s and then you go to 3D. For 4s, it's going to be easier for the electrons to fill the 4s room than it is for you to fill the 3D room. And so then you fill the 3D room last case scenario going up to that section. So you, as a hotel manager, look at it this way. That D room has 5 beds. How many times do you have a room that someone's going to sleep 5 or 10 people in, right? So you're not going to rent out that room until you've rented out the 4s to the couple that comes together, okay? So if I'm looking at, say, vanadium, vanadium is V on the periodic table. I'm going to cross my first 2, so I'm going to go 1s2 for vanadium, and then 2s2. Then I'm going to go 2p6, 3s2, 3p6, and then 4s2, and then finally 3d3. Okay. Now here's the thing with electron configurations. You're going to be sitting here staring at your screen going, what the heck is she doing? And you would be doing the same exact thing in class. True, understandably so. But electron configurations are one of those things that you practice, and then all of a sudden it's like, oh my gosh, it makes sense. I mean, but you have to practice. You have to practice to make it make sense. Okay. Say I wanted to do magnesium. So down here, I'm going to leave vanadium down here. What if I wanted to do magnesium? Okay. Magnesium, I'll use a highlighter this time. And magnesium, I'm going to highlight, I use 1s2, 2s2, 2p6, 3s2. Okay. So for magnesium, I have 1s2, 2s2, 2p6, 3s2. Okay, and that's going to be the electron configuration for magnesium. So again, this is something that you just need to keep practicing with. When we're looking at filling, you could go back and you could look at the periodic table and you could see that you go all the way across as you read the periodic table, just like you're reading a book. So you're going to do 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then you're going to actually do 4f, and then you're going to do 5d, 6p. But what I've done is I've laid that out for you right here, okay? So this is the order in which you're going to fill, okay? And then you add electrons up until you've run out of electrons. So look at the periodic table and figure out how many electrons you need, and then that tells you what your exponents are going to be. Now, something that's important for you to understand, and this is going to be through periodic trends, all noble gases, except for helium, because helium ends in S2, all noble gases are going to end in P6. So if we go back, looking at this, all of these elements are going to end in P6, okay? Those are noble gases. All alkali metals will end in S1. All alkaline earth metals will end in S2, okay? And then all of your transition metals will end in a D, okay? So noble gases will end in P6, halogens will end in P5. So halogens would be like chlorine, bromine, iodine, fluorine. And then alkali metals will end in S1, alkaline earth metals will end in S2. So what can an electron configuration tell you? An electron configuration, if we looked at the very last part of an electron configuration can tell you what the energy level is, what the sublevel is, so the location in the periodic table or the location of the electron, and then how many electrons are present in that sublevel. So if I had something that ended with 3s1, I know that it's energy level 3, so this is the same as the row on the periodic table. And then I know from S1 that that's an alkali metal. So if I go row 3, alkali metal, row 3, 1, 2, 3, 3s1 would be sodium. So really, you could look at the end of the electron configuration, and that'll give you the identity of that element. So another thing that you could do is you could add the electrons together, add all of the exponents, the superscripts together, and that's going to tell you which element it is also, as long as it's a neutral element. So going back to our hotel, and so we have two different things here. We have electron configurations and we have orbital diagrams. So the orbital diagrams are showing exactly, like showing a representation of how the electrons are going to fill those orbitals. The electron configuration itself is just the numbers and the symbols that go along with the location of the electrons. So for example, if I look at lithium, I'm looking at 3 electrons. So right here, I'm going to fill my 1s2. So I put 2 electrons there, and then my 2s1, okay, which is going to be 1 electron there, okay. Then I have beryllium here, boron, carbon, nitrogen, oxygen, fluorine. I've gone all the way up to neon. What if I wanted to deal with, say, sodium? Okay, so if I'm looking at sodium, okay, another way to do this is through a flat line, a horizontal diagram. So I have my 1s, I have my 2s, I have 3 lines for my 2p, and I have my 3s, okay? And so my first two, so sodium has 11 electrons. My first 2 electrons are going to fill my first room with 1 bed, 1s2, and then I'm going to go down to 2s2. So that's 4 electrons. I have 7 left. So I'm going to go 2p, and notice I go across first, and then we share beds right there. So that's going to give me 2p6 and then 3s1. So writing the electron configuration, it would be 1s2, 2s2, 2p6, 3s1. Okay, and that's how you write the electron configuration and how you draw the orbital diagram. Okay, so here's the deal. It's really easy to look at this and go, well, that's a huge waste of time. I mean, why do I have to write out every single one of those? Well, if I look at sodium, magnesium, aluminum, silicon, so I'm going across the same row. If I recognize that, I can see that all of these have 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, all of this stuff. And here's the deal. We really only care about the highest energy level. We only care about what's that highest number. So your highest energy level is going to be the highest coefficient used, the highest number to the right-hand side. And so in this case, it's 3. We only care about those electrons because those electrons are the ones that determine how many spots are available for bonding. So if you think about it, going back to sodium, okay, we still have one space here, right? Or we can give up an electron, which is what actually happens. So now we end up having a full, what's called a valence shell. So valence shell is the outermost shell, and everything wants to have 8 valence electrons or be like the noble gases, which is something we talked about in class. So we can replace all the way up to 1s2, 2s2, 2p6, because remember, all noble gases end in p6. That one applies to noble gas neon. So for this, I could write neon in brackets, and then 3s2, 3p1. For this one, it would be Ne, neon. That represents my 1s2, 2s2, 2p6, and then 3s2. So much easier to write the shorthand. Can you do it all of the time? No, because I'll ask you to do the longhand version. So in this case, Ne, 3s2, 3p2. Okay? So we just talked about valence electrons, but I wanted to make sure that I gave you some clear notes on valence electrons. Valence electrons are the electrons in the outermost shell, and they determine the reactivity of an element. All elements in the same group have the same number of valence electrons, except for helium. So helium is all the way over the noble gases, but in the first energy level, you can only have a maximum of 2 valence electrons. As you go down a group, you add a shell, which means you add an energy level, so the valence electrons get further away from the nucleus. But if you look at the group number, so I've changed the group numbering based on what we did last week. And you see I have Roman numerals. So I have my Roman numerals, okay? So my Roman numerals are the same as my valence electrons. In this group, I have 1 valence electron. In this group, I have 2 valence electrons. In this group, I have 3. In this group, I have 4 valence electrons. I have 5 valence electrons, 6 valence electrons, 7, and 8. And like I've said before, 8 is that magic number. 8 is your stable noble gas, okay? Noble gases are non-reactive. They're not going to end up giving up or sharing or anything. And now there are always exceptions to different things, but really 8 is the magic number. So everything wants to get to 8. But notice that the group number, if you look at this, and these are called the A group, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, that's the same as the number of valence electrons. So you should be able to look at the periodic table for the rest of the year and determine the valence electrons. If there is anything that you're going to have to use all year long, it is this, knowing the number of valence electrons in each element. I'm going to ask you that a lot. Now, core electrons are the inner electrons. They're the ones that determine basically the size and the forces within an atom, but really the core electrons we're not paying attention to when we're dealing with bonding and reactivity. The D block elements typically have 2 valence electrons, or we consider them to have 2 valence electrons because you fill the S sublevel first. And then you go back and fill in the D block. However, You can have up to 5 electrons as considered your valence electrons. We will not use the D block. I won't ask you how many valence electrons D block elements have. Now, Lewis dot symbols. This is the very last thing that we're going to talk about. Lewis dot symbols. What if you don't want to write a whole configuration? What if you really only want to look at how many electrons there are available for bonding? Is there something we can do? And the answer is yes. There's always something you can do. But in this case, you're going to look at your valence electrons, and you're going to look at it as if you have your element, okay? And your element has 8 boxes on the outside. And those are all slots for valence electrons, because remember we said that our stable elements have 8 valence electrons. And so what you're going to do is you're going to fill those spots with electrons. So if you have 1 valence electron, you just have 1. And then notice helium, the only thing, helium is different because you pair up those two. They're going to be an electron pair. But going beyond helium, you always want to go to the sides first. So put 1 electron in each side first, and then you want to fill in. So what I mean by that is you're going to do, like say you had 5. You're going to do 1 and follow my order, 2, and then 3, 4, okay? And then you're going to do your 5th one here, okay? And the reason that you're going to do that, and I lost one somehow, okay? The reason that you're going to end up doing that is because the electrons want to be as far apart from each other as possible. So an example that I use in class is, and it's kind of a silly example, but the boys' bathroom. Because when you go into the boys' bathroom, and girls, you might not know this because I did not realize this before, but you go into the boys' bathroom and say there are 8 stalls. You're going to walk in, the first boy is going to walk in and go all the way to the very end. The next boy is going to walk in and is going to go most likely to like the first stall or the one in the middle. And the reason for that is because boys apparently don't like to pee right next to each other. So they're going to space themselves apart the most that they can first, and then they're going to take up the empty urinals, okay? Now, I do usually have boys at this point in class joke and say, well, no, I would just wait to go to the bathroom because I'm not going to stand right next to someone. And hey, to each their own, but it's a really good example of how your valence electrons are going to end up filling orbitals. So that is it for today. If you have questions as you're moving through your work, as always, go ahead and send me an email. If I need to, I will send you a screenshot. And then I also have another video that I'd like for you to watch because I'd like for you to see this in a different way.